Hello, my name is Hunter. I am a pre-medical post-bac student at Portland State University, and this is a live stream for general chemistry students taking Chemistry 221, I believe. And today we're going to be going over a couple of topics here that will help you as you prepare for your first exam. I'm going to give people a couple minutes to show up just in case we have folks here who want to join live. And for the recording, all of these will be posted to the PSU Learning Center YouTube channel shortly after the broadcast. So if you're unable to join live, but you want to review the recordings, you can do so there on YouTube. All right. If you're here live and you have any questions, feel free to drop them in the chat. I'll try and keep an eye there to answer them as we go. And without further ado, let's jump in. So this is an introductory chemistry class. There are some assumptions made that you may not have encountered many of these ideas before, or at least not to this depth. And so we're going to review very quickly some of the really like broad strokes of the modern atomic theory. And that is simply that all matter is composed of these sort of irreducible components of protons, neutrons, and electrons. Protons and neutrons make up the nucleus of an atom. I'm going to try to keep my stuff consistent here. So we've got protons may be notated like so. Neutrons, I'm going to use a not symbol, and then we'll go with red for our electrons. You might see it notated like that. And these are going to be my electrons floating around my nucleus. So for a neutrally charged one proton, one neutron, and one electron that is orbiting my nucleus, we can determine its identity because that would be a hydrogen. Hydrogen has one proton, one neutron, one electron. Cool. So that's a lot of information to write. Oh my goodness, I'm realizing my face is covering this now. So protons, neutrons, and electrons. So because that's a lot to write, we've come up with these shorthands, these notations that allow us to convey a lot of information very, very quickly. And that's what you see in your periodic table, which I'm going to drag this down into the window here so you can see it. ptable.com was a really helpful resource for me when I was in the general chemistry series. And you can explore this on your own time, but you can click on any individual atom and it will give you a lot more detail over here on the left. You can also change some of the sliders on here so that it will show you different information and give you different color gradients that I found super helpful. All right. So I have my sort of talking points up here pasted at the top. This is just going to help us guide how we talk about this, and we'll get to discuss this more as we get into the problem set. But in your textbook, and I've included a couple of links here in the presentation, your textbook has all of these images as well. So the difference between a binary molecular and an ionic compound. Binary molecular simply means that it's binary. It has two components. Molecular, more than one atom. And compounds is just very broadly a term that refers to maybe many, many atoms together, bound together. And so for ionic compounds have some unique properties. For example, we'll do sodium chloride, and this is I'm doing this off on the right again where you can't see it. So sodium chloride has some interesting properties where we have an alkaline sorry, yes, so we have an alkali metal. I'm going to put that over here in group 1. Is that labeled on here? It is not. So sodium has a charge of +1, and chlorine, which is over here, has a charge of -1. Those charges balance each other out. They exist in these charged states in nature. And so when they form, and so they're attracted to each other. It's sometimes helpful to think of this in terms of opposite poles of a magnet, where positive charge is attracted to negative charge, and they come together and sort of share space and share charge. That's a useful way for thinking about them. And that creates a compound with a net neutral charge. So that would be an ionic compound, where no covalent bonds are formed. So we're going to keep that in the back of our heads. We're going to move on. When we are looking at the periodic table, we can make some predictions about what the charge is going to be on these atoms based on their proximity to this group right here, the halogen, or the noble gases. So the noble gases always, in their natural state, have a net charge of 0. And you can see that notated here. There's no charge notated on here. But if we go 1 to the left, we see that the entire column here has a -1 charge. So in their natural states, these exist with a -1 charge. If we go 2 to the left, they have a -2 charge. This is the oxygen group. And I guess they have a special name, which I've never used outside of this context, which I believe is pronounced chalcogens. And then if we go one more group to the left, these are the nitrogen elements, and they have a -3 charge. Carbon then has that -4, but it's kind of unique. So you will come back to carbon later in your chemistry career. So again, we're starting at the noble gases. Each column we go left, we have a difference in charge of -1 from the last one. Now, if we go the other direction, we have to think of this as a continuum. That would bring us back over to the left side of the periodic table here, and these are our alkali metals. And these have a +1 charge. You go another one to the right, you have a +2 charge. The rest of these groups are really variable. Some of them are pretty consistent, and you can see those noted here. But chromium, for example, can be +3 or +6 charge, which will be important later. So that's kind of an intro in how to read this and make predictions about what charge certain elements are going to have. This table is also from your textbook. These are common polyatomic ions. It would behoove you to memorize most of these at some point. If you're like me, that is sort of going to happen naturally the more that you interact with this material. It's not like I sat down and memorized this entire table, though you certainly can, and I had classmates who did that. So, digging into the exercises. We're going to start with number 11 here. Write the symbol for each of the following ions. So I'm just going to create a little square as if this is on our periodic table. We've got an ion with a +1 charge, an atomic number of 55. Make sure I've got that right. No. Yes. Atomic number of 55 and a mass number of 133. So the atomic number is what's really important here. This tells you specifically the number of protons that are in our nucleus. Remember, these are our protons. There are 55 protons in this nucleus that make it pretty heavy. So you can then go back to your periodic table. There. 1 is up here, 3 is here, 4, 5, 6, 7, 8, and so on. 55 is right here, and that would be cesium. Oh my goodness. So the identity of this element is cesium, CS. So you can notate it this way as if it's on the periodic table. You can also write this like so. Both are correct. Both convey the same information. Cesium has 55 protons is implied because the number of protons um, determines its identity, and then its mass number is 133. We can take 133 minus the number of protons will equal the number of neutrons. And I know this is easy math, but I'm in the habit of using my calculator for absolutely everything. It would be 78 neutrons. So that'll be handy later. 11b, the ion with 54 electrons, 53 protons, and 74 neutrons. So we're given a little bit different information here, right? We've got 53 protons. Again, that determines its identity. And then we're told a number of electrons and a number of neutrons. Electrons are so tiny, they don't have much mass. And when we're working at this scale, we can kind of ignore them for now. So again, we have this formula where we have the mass number plus the minus the number of protons equals the number of neutrons. We can use that formula to figure this out by doing a little algebra. So 53 protons plus 74 neutrons equals our mass number. 7, 10, 12, 127. Is our mass number, so 127. And is there a charge associated with this? Now this is where the number of protons and electrons becomes important, because if the protons and electrons are in balance, then the charge is neutral, remains neutral, they cancel each other out. Because we have one more electrons than we have protons, the charge is going to be negative. So we have negative 54. How would I note this? Yeah. Positive 53 gives you a -1 charge. And so we would put a negative in the top right corner there. This atom would be iodine, which is notated simply by the letter I. And equally, you could write that as iodine 127 would be its identity. Cool. Next up, we have an ion with an atomic number of 15. Excuse me. Mass number 31, and a -3 charge, 3 negative charge. So again, 15 is our identity. We can look, that's the number of protons. That would give us phosphorus. Phosphorus, notated by P. Mass number of 31. So 31 minus 15 would be 16. That gives us the number of neutrons and a -3 charge. It's not asking for that information, but that is good to be in the practice of kind of intuiting what that means. Next up, ion with 24 electrons, 30 neutrons, and a 3 positive charge. So we're not given a number of protons. We don't know what the identity of this is yet, but the other information can kind of help us get to the answer. So we have 30 neutrons. We have 24 electrons and a 3 positive charge. We know just by looking at the number of electrons that to get a 3 positive charge, we need 3 more protons than we have electrons. So our number of protons, going to be 24, 5, 6, 7, which gives us an identity. 27 would be cobalt. 3 positive charge, and then number of protons plus number of neutrons is 57, is our mass number. So far, so good. Just check on the chat, see if we have anything going on. Looks good. All right. Give the number of protons, electrons, and neutrons in neutral atoms of each of the following isotopes. So isotopes are a little bit different. They don't have a charge, but they are different from what might appear on the periodic table. And we'll dig into a little bit of what that looks like here. So number of protons, electrons, and neutrons. So for A, we've got protons, neutrons, and electrons in neutral atoms. There's no charge. So what we know from that by definition is that the number of protons and the number of electrons are going to be the same. So we've got lithium here. And now I'm looking at this and I feel like, nope, this is just a different notation. So this is one that I haven't interacted with as much. This notation that looks like the, now I feel like I've got it backwards. Let's look here. Yep. I apologize. So, all of this information is correct except for the location that I put the mass number and the atomic number in. Those need to be reversed. So if you're following along here, the atomic, yes, the atomic number goes in the bottom left corner and the mass number goes in the top left corner. My apologies. So it should look more like the notation that we see here in question 19. So our atomic number for lithium is 3. By definition, protons give us our identity. We have 3 of them. We have 3 of them. Our atomic mass is protons plus neutrons. We're given 7. So the number of neutrons must be 7 minus the number of protons, so minus 3. Give us 4. So 4 neutrons. And this is a neutral atom. Number of electrons matches the number of protons. Same drill, 125. And I'm looking because we don't deal with these as often. Is it tellurium? It's not even on this table. That's exciting. We're given 25 protons. Since it's neutral, we know that it has 25 electrons. And the number of neutrons is going to be 125, which is our mass number, minus 25 would be 100. See, we've got Ag. Ag is silver. which is a little bit weird. Makes sense if you know the Latin, I think. We're given 47 protons. It's neutral, so we know we've got to have 47 electrons. And a mass number of 109 minus 47 gives us 62. And so on and so forth. Moving on, let's take a look at number 24. So variations in average atomic mass may be observed for elements obtained from different sources. Lithium provides an example of this. The isotopic composition of lithium from naturally occurring minerals is 7.5% lithium-6 and 92.5% lithium-7, which has masses of 6.05 AMU, 0.15 AMU, and 7.016 AMU, respectively. A commercial source of lithium recycled from a military source is given as different ratios of that. So calculate the average atomic mass values for each of these two sources. To answer this question, you have to know this equation right here. The average mass is the sums of the fractional abundance of each isotopic mass. Let's take a look at how to do that. Actually, I've included links here to where you can find the walkthroughs in the textbook. These aren't clickable in the live stream for you guys, obviously, but this is what it looks like in your textbook. I highly encourage that you use that resource. All right. We're starting with naturally occurring. 7.5% lithium-6 and 92.5% lithium-7. So we've got 7.5%. How do I want to write this? We'll do it this way. Times lithium-6, which has a mass of 6.01512 AMU, plus 92.5% times 7.0166 AMU. I don't have my scientific calculator close by. Right. Nowhere to be found, so we'll make it work. 0.075 times 0.075. Paying attention to significant figures. Here we've got 2, so we're just going to carry those 2. Do that right. Okay. And here we've got 3, so 6.49. There's my 3 significant figures. So sum those up. 6.94 AMU. And we keep those three significant figures because we have 2 decimal points here in 0.45. So that's our average mass of the naturally occurring lithium. Make this a little bit smaller here. And now we have our unknown, the commercial. We're given 3.75% of lithium-6, and again, that was 6.015. Plus, and the rest was lithium-7. So that would give us 96.25. Plug and chuck, do the math. Gives us a final answer of 6.979 AMU commercial, which is a little bit heavier than the naturally occurring isotope. All right, so for number 48, for each of the following compounds, state whether it is ionic or covalent, and if it is ionic, write the symbols for the ions involved. The way that you solve this is by going back to that periodic table that we looked at earlier, where we had the charges notated based on how far it was from the noble gases. So if you have an alkali metal and a non-metal in a compound, it is probably an ionic compound. So we have, these two components, and to really recognize these, you need to have looked at that chart and you need to know your periodic table pretty well. Potassium is an alkali metal. Potassium has a charge of, I believe, 1. Yes, because it's in that group 1 element. So potassium has a positive 1 charge. And ClO4, if I'm not mistaken, is chlorate. Let's take a look at that table again. ClO4 is perchlorate and has a negative 1 charge. If you only knew that potassium had a positive 1 charge, you could intuit that perchlorate has a negative 1 charge because this ionic compound is neutral and because there's only one of each. So looking at this next one, we have manganese or magnesium. Magnesium. Magnesium is an alkaline earth metal. And it's in that group 2, so it has a positive 2. This properly would be 2 positive. Now, this notation here means that there are, everything in parentheses, there are two of those. So we have 2 C2H3O2. To get to a positive 2 charge, 2 of those must each have a negative 1 charge. CH3O2 because I don't have this one memorized. It's a carbohydrate. What is it? Oh, this is acetate. This is acetate. The reason it's confusing is because you usually see it written based on its atomic structure and how they're bonded to each other, which is this. But it's the same thing. 2 carbons, 3 hydrogens, 2 oxygens with a negative charge. So this would be magnesium acetate. Hydrogen and sulfur. This one's a little weird. And it's weird because we don't talk about, hydrogen is not an alkaline earth metal, even though it appears in that group 1, right? So hydrogen does have, generally, a positive charge associated with it, and sulfur has a negative 2 charge. So this one, actually not. This would not be an ionic compound. This would be a covalent bond between the hydrogens and the sulfur. So Ag again, we have silver, and we have sulfur again. Looking back at this table, silver does have a positive charge associated with it, right here. Sulfur has a negative 2 charge associated with it. Looking back at our problem, it's a neutral charge. We have 2 silver, we have 1 sulfur. 2 silver, 1 sulfur. That's going to be a tongue twister. I want to be 100% crystal clear that I'm telling you guys the right thing. So, silver is a metal, sulfur is not. This would be an ionic compound. Silver has a positive charge. Sulfur has a negative 2 charge. Nitrogen and chlorine. So nitrogen, not being an alkaline earth metal, this is probably not an ionic compound. Here we have cobalt and nitrate. So nitrate, remember, has a negative 1 charge. Since there are 2 of them, we can intuit that the cobalt has a positive 2. Yes. 2 positive charge. Cobalt is a metal. This is an ionic compound. And again, the big hint here is whether or not a metal is present, including alkaline earth metals. So for each of the following pairs of ions, write the formula of the compound they will form. So here we're given the ions in isolation. In the previous problem, we were given the compound itself. Here we're given just the ions. The way that we figured this out is we want something with a neutral charge. So we have calcium with its +2 charge and sulfur with its -2 charge. Those will come together and balance out in a 1-to-1 ratio. Calcium sulfide. Here we have NH4 is ammonia. Ammonia, ammonia. It's ammonium. And SO4 if SO3 is sulfite, this must be sulfate. Sulfate, yes. Ammonium has a +1 charge. Sulfate has a -2 charge. We need 2 ammoniums and 1 sulfate. So let me look here what they think about ordering these. Yeah. Two ammoniums per sulfate for each sulfate. Got to be precise in our language here. Same story. Aluminum has a +3 charge. We're going to need 3 bromines to balance those out. And so on. Okay. Looking at our time, we're doing just fine. We're just going to do 1 or 2 of each of these. I want to make sure you get some practice on each of them. So write the formulas of the following compounds. So rubidium bromide. Let's take a look at our periodic table. So rubidium is an alkaline earth metal in group 1. So it has a +1 charge. Bromine is a halogen. So it has a -1 charge. Halogen is 1 step to the left of those noble gases. So this would simply be rubidium bromide. No modification necessary. Magnesium selenide. Magnesium has a +2. Selenium also. Selenium has a -2 charge. So that would be magnesium selenide. Sodium oxide is pretty straightforward. Sodium's in group 1. Oxygen is 2 over. So you're going to need 2 sodium per oxygen. Yeah. Cool. 54, write the formulas of the following. So lithium carbonate. So this again, it's going to be really helpful to have that chart handy and to memorize these as you go. Lithium's in group 1. Carbonate has a 2 negative charge. So we're going to have lithium 2, carbonate. Carbonate is CO3. Similar story, sodium, perchlorate. Perchlorate, ClO, there's 4 of them. Yeah. Perchlorate has a -1 charge. Barium has a +2. Hydroxide, I think, has a -1. Yeah. All right, 57. Each of the following compounds contains a metal that can exhibit more than one ionic charge. Name these compounds. So I mentioned at the beginning of this live stream that chromium has a couple different possible charges and that would be important later. Our moment has come. So chromium oxide. Chromium oxide is really like a really pretty compound. It's bright green. So this chromium oxide is used, it's also fairly non-toxic, even though chromium is generally on its own pretty reactive. And so this is used in a lot of cosmetics where you want like vivid green. It's also used in making jewelry as a fine polishing compound. And the more you know. So chromium oxide, oxygen, generally speaking, has a -2 charge. And there's 3 of them. So we have to make up for a -6 charge. So chromium must have, in this case, a +3. This must be chromium 3. So the way we would write this name these compounds. So this would be chromium, and we use Roman numerals 3 oxide, chromium 3 oxide. We're going to skip ahead because in exercise C we have chromium oxide again, but this time we just have 1 chromium. So it must be that we have chromium 6 oxide. Because that 1 chromium is making up for all 6 of those negative charges that come from the 2 negative oxygens. All right. Titanium chloride's another easy one that we should just do. Chlorine has a -1 charge. There's 4 of them, so it must be titanium 4 chloride. Yeah, cool. And finally, the following ionic compounds are found in common household products. Write the formulas for each compound. Same thing in reverse. So we have potassium phosphate. So we know we have potassium. And phosphate is PO4. You have to know that phosphate has a 3 negative charge on it, and that potassium has a +1. And so you're going to need 3 of those potassiums to counteract the 3 negative charge of the phosphate. Similar story with copper. So copper 2, we're told right away what the charge is on this because copper is another one of those that can have multiple charges. So copper 2 has that 2 charge on it. Sulfate also has, sulfate has a negative 2 charge on it. Yep. Oh, copper sulfate, excuse me. This is where reading very carefully will save you. Yes, sulfate has a 2 negative charge. This copper has a positive 2 charge on it, so we're done. Copper sulfate. Cool. Alrighty, we're at about 46 minutes. Generally, I like to give a little outro, which is that these live streams, the workshops, the tutoring center were all really helpful resources for me when I was encountering this information for the first time. You can see I'm a little rusty on it. I haven't needed it for coming up on a year now. I used it when I took the MCAT last year, and I have put those study study materials away. So I apologize that I'm a little bit rusty. I will be better prepared for next week. So thank you for your patience on that. But all of these resources, the tutoring, the live streams, the workshops, were all really, really, really helpful for me in learning how to develop better study habits as a returning student. If you have any questions for me, you can find me, you can contact me directly at hlea@pdx.edu. Happy to talk about it, whether your questions are study related, school life related, finding balance. Please don't hesitate to reach out. If I can't help you, I can direct you to someone who probably can. And with that, enjoy the rest of your Friday. Have a great weekend. Hope to see you next week.